Hello all, today we're going to be looking at alternating series because some funky things happen when you throw in a -1 raised to the n power, and even though it doesn't seem like there's a -1 to the n power right here, there really is, because I can split up that 1/3 and the negative into its own thing. So anytime you see a -1, it's usually an alternating meaning it's going back and forth between negative and +1 there. So when we have an alternating series, some funky things can actually happen, and we want to take a look at what is happening with our series part and then our alternating part. So we can say that our alternating series converges as long as our terms keep on getting smaller, and so you can see 1/2, 1/3, 1/4, not the negative part, but just the absolute value part, just the sequence part of it. Those are getting smaller, so check. And then also our limit of that sequence, so in this case this would be the sequence of 1 over n as n approaches infinity for this problem up here, that has to equal 0, which in fact this does equal 0. So this function up here, even though without the -1 it's harmonic and it does not converge, with the negative alternating back and forth it does. And I want us to kind of look at a diagram of that. Okay, so this one is straight out of our textbook, and this has a special name because it's so kind of freaky weird. It's the alternating harmonic series. So the harmonic part is the 1 over n, and the alternating is the -1 raised to the n, or -1 raised to the n+1 in this case that we have here. So if we think about our terms, I have 1, and then normally I would just keep on adding 1/2 and 1/3 and 1/4, but because of that negative, we're actually subtracting 1. So I've added 1, and now I'm subtracting 1. And now I'm adding 1/3, and now I'm subtracting 1/4 from that, and then I'll be adding 1/5, and then I'll be subtracting almost 6 from that. And so you can see that this sequence will actually converge on something that is between 0 and 1. I want to look at a more animated picture of that. Okay, so I know this kind of looks crazy, but our n value is what sequence or what number our sequence is. So if I plug in 2, I would have -1 to the 2. I would have, -1 to the 2 plus 1, so it'd be -1 over 1/2. So you can see it's a 1/2 right here. And then when I plug in 3, it's going to be positive 1/3, and this is my summation that I have. So S is equal to the summation. And then when I plug in 4, it's going to be -1/4. Then that's the summation of all 4. 5, it's going to be positive 1/5, -1/6, positive 1/7, -1/8. And you can see as I am going back and forth, it's actually starting to settle on some value, which is weird. It's like right below 0.6, and we'll actually figure out what that is. Not today, but in the future. So I want us to look at a few examples of things that maybe would fit the alternating series test. So remember, there has to be something that is alternating. So out of these 3 categories right here, I do not see a -1 to the n power in this one. So this one is just not alternating. Not alternating whatsoever. Now, these ones actually will, and to get a good sense of what's going on, I'm actually just going to plug in some values. So if I plug in 0, anything to the 0 power is 1. -1 to the 1 power is -1. And then -1 to the 2nd power is 1. And you'll actually see this pattern of this is alternating for sure, but there's some things that are wrong, because if I take my limit of this sequence, it's not going towards anything. It's just alternating between back and forth between -1 and 1. So my limit does not actually exist. My limit isn't 0. And then another problem that we have is that first condition where all terms after have to be getting smaller, so they have to be decreasing, and these are not decreasing over time. So no for our alternate series test, at least. Well, maybe this one actually will. So I have alternating, cool. Is this decreasing over time? I'm going to have and I'm just thinking about the part without the -1 to the n. So 1 over ln of n. So I'd have 1 over, I don't want a 1 in here because that would be division by 0. So I started at 2. So I'd have 1 over ln of 2. comma 1 over ln of 3. So my denominator is getting bigger, but it's 1 over that number, so it's actually going to be my 1 over. My sequence part of this is actually going to be getting smaller. And we can also say that my limit here of 1 over ln of n is actually going to 0, because I'm going to have 1 over a pretty large number. So this one does actually fit our alternating series test, so this one is actually going to converge. Okay, last example to kind of talk about, here is my alternating part. So I just really want to look at my n over n squared plus 1. And we need to see, not if that converges, but just see if our limit of this as n approaches infinity is going to be 0. And sure enough, our denominator is way bigger. It's a squared instead of, so cubic instead of linear. So this is going to equal 0. So that's good. And now let's actually look at our consecutive terms. So if I look at plugging in 1, I would have 1 over 1 squared plus 1, so 1 over 2. My next term, if I plugged in n equals 2, I would have 2 over, let's see, 2 squared plus 1 is going to be 5. If I plug in 3, I would have 3 over, and then 3 squared plus 1, so that would be 10. So you can see these terms are actually also decreasing. So this one was larger, this one was larger, and they're going to be decreasing in size. So by the alternating series test, this also converges too. Okay, this next kind of part took me a little while to actually wrap my head around, but basically it's really not too bad to find remainders for alternating series because of this back and forth motion that is happening here. So because they're always decreasing, so our sequence itself is decreasing and we're alternating between positive and negative, if I'm looking at this term right here, this b sub 4 term, and I was looking at, I don't know, my summation of all 4 of those terms, well, basically, all I would have to do, boop, 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 is look at what my b sub 5th term is going to be, and all of the how far I am off by this is going to be contained in that b sub 5. So my remainder for my 4 first terms is going to be smaller than just my next term in the sequence. So going to be smaller than my b sub 5th term, because b sub 5 is going to contain all of my addings and subtractions from there on out. Okay, so we're saying later in this course, but it's actually just going to be in about a week or two that we're going to be talking about Taylor series. They're actually super cool and honestly kind of crazy. They blow my mind. So if we're looking for remember this is our alternating harmonic series. If we're looking for an example right here of what our error would be. So find an upper bound. What would our error be after the 99th term? Remember, all we really need to do is actually look at what our 100th term is in the sequence. So I'm going to look for my next term in the sequence. So b sub 100 is actually going to be an estimate for my error. And that's my remainder after the first 99 sums. So if I'm looking for my 100th term, all I really need to do is just plug 100 into my just this part, just into the sequence part of that. So I'll have -1 to the, and this part actually doesn't really matter because we want to actually take the larger of the values that we could get. So no matter what, this is just going to be a positive 1. So I'll just have a positive 1 over, and then my b sub n. So I'm looking at just the series without the alternating part. So this is just going to be 1 over 100. So a good bound for my remainder would be 0.01. This would be my upper bound for my error. And I actually want to figure out what that is. So I'm going to look at my first 99 terms of -1 of my alternating series that I have here. And I actually know that the infinite sum of these is going to approach ln of 2 exactly. So ln 2 is the exact value. So this is how far off. This is our actual error. And that is going to be, that is smaller than the upper bound that we found. So we found 0.01. This is smaller than that, but it's still a bound that we can have. So we can still see that this is still a bound for that value that we came up with for the actual error. This is actually a continuation, or yeah, it's actually a continuation of this. So there's supposed to be an ln of n right here. So we're saying, okay, now we know what we want our remainder to be within. So how many terms do we need to add together? So again, I'm not really paying attention to my alternating part. I'm really just paying attention to my 1 over ln of n part. And what I want to do is I want to say, hey, I know that there's some n that when I just go 1 past it, when I go 1 past that n value, I'm going to be within the 0.01 that I have here. So this is like my r sub n that I would have right here. This is my remainder that I would have after. And so I wanted to go just one more, and now this is turned into an algebraic function that I can actually solve here. So I'm going to multiply by ln of n plus 1 on both sides, and then divide by 0.1. And now I'm really just trying to solve for this n, so I'm going to raise both sides to the power of e. I will have e to the power of 10 is less than n plus 1. And last thing I need to do is actually subtract 1. So n just has to be larger than this really crazy number, 22,025.4. And n has to be larger than that. So even though normally we would round this number down, it's a decimal, we are actually going to round it up because n has to be larger than that, and it also has to be a whole number. It can't be part of a whole. This is extra. There's not actually any homework that is going over this specific thing, but I just thought it was interesting. Okay, last kind of thing that we're going to talk about is, well, we have these, like the alternating harmonic series that converges when it's alternating, but doesn't converge when it doesn't have that -1 to the n power. So when we take away the alternating part, it doesn't actually converge. There's a distinction between this. We call this absolute convergence. If both the series converges with the alternating part and it converges without the alternating part. And then we call it conditional convergence if only the part with alternating, the -1 to the n part, converges, but the other one doesn't. So for example, I was just saying a bunch of stuff. So when I take my absolute value of this, my alternating part goes away, and this thing diverges. So this is only conditional. This has conditional convergence. It depends on this -1 to the n power being in there. But if I look at still taking my absolute value of that, so 1 over n squared, this also converges. And so whether it has the alternating part in it or it doesn't, it still converges. We call that absolute convergence. And our last example right here, it also converges absolutely since it converges and all of its terms are already positive. So if we have absolute convergence, then it's implied that we have conditional convergence. But it doesn't work the other way. It doesn't work the other way. So like this way it works. This thing converges without the alternating part, so when I add in the alternating part, it's already going to converge. And the reason why it doesn't work the other way, the reason why is it matters how we actually add things up. So when we're saying conditional convergence, we're saying, hey, this sum right here, what if I actually just looked, like, what if I rearranged these? What if I didn't have plus minus plus minus plus minus? What if I actually put my positives together and I threw these all positives together right here? And so you can actually see when you rearrange all the positive ones first, you're going to end up adding an infinite number of of positive values, and this infinite number of positive values is actually going to diverge. And then you're going to be subtracting, but it already has diverged. It's already gone through infinity. So this condition, we're saying it's conditional on how we actually add it together, whether we add it plus minus, or we throw all of our negatives and all of our positives together. Kind of weird. But weird stuff happens towards infinity. This is a great summary. So conditional convergence, it means that it's order dependent, but absolute convergence, the order doesn't matter. We can switch terms, we can do anything we want. It'll always absolutely converge. Okay, we have our problems right here. So remember, when you are looking at these, what we're really trying to see is if it does absolutely converge, then our term without the alternating part will also converge. There are two of these. There are two of these that absolutely converge. So there are two that absolutely converge, and there is one that conditionally converges on this page. Okay, my other hint on number 4 especially, it says rationalize the denominator, and you're like, what does that mean? There is no rationalizing, there is no denominator. So what we can really do is we can actually multiply by the conjugate, which is a plus instead of a minus here. And if we do that on the top and the bottom here, we will actually get something that we can't compare to using our limit comparison test of 1 over square root of n. So that is my hint, is follow this through, and then we can compare it to this with our limit test, and so that would be what we'd have on the denominator. Okay, y'all, that is all of my hints, and I hope you have a beautiful day. Bye.